July 2025, a citizen astronomer captures a flicker of metallic light racing across deep space, setting off a frenzy of speculation. Days later, Atlas confirms the impossible, an interstellar comet far larger, faster and stranger than anything seen before. Within weeks, the world's most powerful telescopes record something even more disturbing. Bizarre metal anomalies around 3YYE/Atlas, quadrupling in intensity, with surges of nickel vapor and growing clouds of poison expanding on a scale never observed in any comet. NASA scrambles to monitor the risk to Mars as speculation explodes. Could these signals point to new physics, or perhaps engineering not of this Earth? The lines between rumor and reality are blurring, and the search for answers is only just beginning. Miguel Santos, an amateur astronomer in Lisbon, spent the night of July 18th hunched over his backyard telescope, chasing a fast-moving object flagged by the ATLAS survey just weeks prior. Around 2 a.m., his camera caught a sequence of images that left him staring at the screen in disbelief. A shimmering, metallic glint embedded within a diffuse reddish halo, set against the blackness of space. He posted the raw frames online within hours, tagging them #3IATLAS and inviting anyone with a telescope to confirm what he saw. Within a day, his thread exploded across social media. The original post racked up over 80,000 reposts and comments, drawing in everyone from seasoned astrophotographers to science fiction fans. Some pointed out the comet's sudden expansion, measured at 13,000 kilometers wide in his first image, ballooning to nearly 18,000 kilometers by July 21st. Others zoomed in on the bright specks near the core, debating whether they were cosmic rays, camera noise, or something stranger. "Looks like metal," one comment read, racking up thousands of likes. Another user replied, "That's no artifact, the glint is real." Skeptics arrived just as quickly, dissecting Santos's exposure settings and calling for calibration data. A few accused him of chasing viral fame, but the debate only fueled more uploads. By the end of the week, a loose network of citizen astronomers from Tokyo, Cape Town, and Buenos Aires had posted their own images and time-lapse videos. Each confirmed the same pattern. The coma was growing at a rate no one could explain, and the metallic flashes kept multiplying, quadrupling in visibility and number within days. Major astronomy news outlets picked up the story, amplifying the controversy. Some headlines called it the Lisbon anomaly, while others warned against jumping to conclusions before the professionals weigh in. Hashtags like #mysterious metal anomalies and #quadrupling space objects trended for days, drawing in experts and trolls alike. The split was clear. Half the community dismissed the images as overprocessed, while the other half demanded answers from observatories and space agencies. Santos, meanwhile, became a reluctant figurehead. Interview requests flooded his inbox. He posted screenshots of his calibration files, timestamps, and raw data, insisting he wanted only the truth. "If it's real," he wrote in a follow-up post, "someone with a bigger telescope will see it soon." The grassroots frenzy pushed professional astronomers to act. Observatory inboxes filled with tips and requests for confirmation. The world's largest telescopes began to turn their gaze toward 3I/ATLAS, searching for proof behind the viral claims. The line between amateur discovery and scientific investigation blurred as a backyard observation in Lisbon set off an international race to solve the mystery. On July 1st, 2025, the Atlas survey pipeline flagged an object with a trajectory unlike anything cataloged that year. The coordinates, relayed to the minor planet center, described a hyperbolic orbit, its velocity and path confirming it would never return to the solar system. Within hours, the Atlas team at the University of Hawaii issued a global alert, triggering a cascade of automated notifications to observatories across 3 continents. Astronomers at the European Southern Observatory, the Pan-STARRS network, and the Las Cumbres Global Telescope Network all scrambled to secure observation windows, knowing that early data would be critical for classification. The initial diameter estimate, based on reflectance and brightness, suggested a nucleus over 5 kilometers across. That alone set off a quiet urgency among professionals. Neither Oumuamua nor Borisov approached that scale. The orbital solution, calculated by Dr. Peter Varish at the Harvard-Smithsonian Center for Astrophysics, confirmed a hyperbolic excess velocity, nearly double that of previous interstellar visitors. The object's inbound speed, combined with its steep trajectory, left no doubt. This was the third confirmed interstellar body, now officially designated 3b/Atlas. The Atlas team coordinated with the Space Telescope Science Institute to request an emergency observation slot on the Hubble Space Telescope. Within 36 hours, Hubble's schedulers approved a target of opportunity observation, rearranging a week's worth of planned science to prioritize the new arrival. The first Hubble images, captured on July 3rd, immediately corroborated the ground-based reports. The coma's reddish halo and the bright, unresolved core matched the viral amateur images, but with far greater clarity and signal-to-noise. These data were shared in near real time, with the International Astronomical Union's Minor Planet Center activating a global data-sharing pact that ensured all incoming observations, photometric, astrometric, and spectroscopic, would be pooled for rapid analysis. As the international network mobilized, teams at the Very Large Telescope in Chile and the Gemini Observatory in Hawaii queued up follow-up spectroscopy. The aim was to measure the object's velocity, reflectance spectrum, and coma morphology with the highest possible precision. The community's response was swift and methodical. Each new dataset was uploaded to shared repositories, cross-checked against the Atlas pipeline's initial findings, and flagged for anomalies by automated scripts and human reviewers alike. By July 4th, an unprecedented volume of data was flowing between institutions. The first round of official circulars, released by the Central Bureau for Astronomical Telegrams, confirmed that the object's speed, trajectory, and brightness could not be explained by any known solar system comet or asteroid. The world's largest telescopes had, in less than a week, validated what began as a backyard discovery. The process, alert, confirmation, and coordinated follow-up, demonstrated the reach of modern astronomical networks and the speed at which a single anomaly can become a global scientific priority. Harvard's Center for Astrophysics released their first mass estimate for 3b/Atlas just days after the initial Hubble images. The number stunned the scientific community: 33 billion tons. For comparison, that's more than 3,000 times the mass of the largest comet ever recorded from our own solar system. The nucleus, calculated at over 5 kilometers across, dwarfs both Oumuamua and Borisov. Yet the true surprise came from how this mass was inferred, not through brightness alone, but from the comet's stubborn resistance to non-gravitational acceleration. Dr. Richard Cloete and his colleagues at Harvard spent hours running dynamical models, comparing more than 4,000 astrometric measurements from 227 observatories. They expected to see subtle shifts in the comet's path, telltale signs of jets pushing it off course as the sunlight vaporized ices. Instead, the orbit remained almost perfectly smooth. The only way to account for such stability, given the observed outgassing, was to assign the nucleus an extraordinary bulk density. Avi Loeb, a senior astrophysicist on the team, called it a statistical outlier, an interstellar object so massive that some researchers wondered aloud whether it could even exist by known natural processes. While the Harvard group's findings drew skepticism from modeling rivals at Caltech, who questioned the assumptions about outgassing direction and internal structure, the raw numbers spoke for themselves. Even with conservative error bars, 3i/Atlas stood out as an anomaly. The comet's mass and density made it not only the heaviest interstellar visitor on record, but also one of the most physically robust bodies ever tracked inbound from deep space. Simultaneously, attention turned to the object's coma, the vast, glowing envelope of gas and dust surrounding the nucleus. Within 72 hours, ground-based and space telescopes documented a rapid expansion, from 13,000 kilometers wide in the earliest amateur images to 18,000 kilometers by July 21st. That kind of growth, a 38% increase in just 3 days, is rarely seen even in the most active solar system comets. The reddish hue, confirmed by Hubble's high-sensitivity cameras, suggested a complex mixture of organic compounds and dust grains, possibly altered by interstellar radiation before entering the solar system. Harvard's modeling team published their preliminary results on an open-access preprint server. Their analysis included side-by-side comparisons of coma morphology, brightness profiles, and non-gravitational force calculations. The data pointed to a nucleus so dense that even aggressive outgassing, estimated at over 150 kilograms per second, barely nudged its trajectory. For planetary scientists, the implications were profound. 3I/Atlas was not only breaking records for size and activity, but also challenging the very models used to understand comet evolution and interstellar transport. The object's sheer bulk and the explosive coma growth forced a new round of questions about what's possible for bodies born beyond our solar system. As the world's telescopes continued to track the expanding cloud, Harvard's findings set the stage for the next puzzle: the chemical composition of the coma itself and the metallic signatures that would soon create even deeper mysteries. On April 3, 2025, Dr. Lena Vukovic, a spectroscopist at the European Southern Observatory's Very Large Telescope, stared at her monitor as the latest data streamed in from 3I/Atlas. The spectrum revealed a sharp, unmistakable signature: atomic nickel, bright and persistent, with no trace of iron. In comet science, nickel and iron are inseparable companions, both forged in the same stellar furnaces, both expected to vaporize together as a comet nears the sun. Yet every calibration, every cross-check, confirmed the same result. Nickel lines at 3,520, 5,587, and 6,767 angstroms stood out with signal-to-noise ratios above 25. Iron remained stubbornly absent, below the detection threshold by at least 2 orders of magnitude. Dr. Vukovic's initial reaction was caution. She messaged colleagues across time zones, suspecting a data artifact or a quirk in the reduction pipeline. But replies came back from the JWST team and Gemini North. Their independent spectra showed the same anomaly. By August, the James Webb Space Telescope's NIR SPEC instrument measured nickel vapor escaping from 3I/Atlas at a rate of 4.6 grams per second. No instrument, from the Hubble Space Telescope's ultraviolet channels to ground-based arrays in Hawaii and Chile, could find a matching iron line. The nickel-to-iron ratio exceeded 100, dwarfing the typical values near unity seen in solar system comets and meteorites. The implications rippled through planetary science circles. In normal cometary outgassing, iron and nickel are liberated together in nearly fixed proportions, reflecting their cosmic abundance. For 3I/Atlas, the absence of iron alongside such abundant nickel defied every known natural mechanism. Laboratory spectra ruled out complex nickel-carbonyl compounds, and calibration checks across 4 major observatories eliminated the possibility of an instrumental error. As Dr. Vukovic summarized in a late-night call, no known comet, asteroid, or even star-forming cloud has ever shown a nickel-to-iron ratio like this. While the nickel puzzle dominated professional debate, another anomaly surfaced in mid-September. The James Clerk Maxwell Telescope, monitoring volatile gases, recorded a surge in hydrogen cyanide production. On September 7th, the outgassing rate measured 1.5 times 10 to the 25th molecules per second, a typical value for a large active comet. 7 days later, the rate had leapt to 4.5 times 10 to the 25th molecules per second, nearly quadrupling in less than a week. Operators repeated their calibration, suspecting instrumental drift or interference, but the spike persisted across all systems. The cyanide-rich coma stretched 180,000 kilometers, forming asymmetric jets that rotated with the comet's spin. The combination of pure nickel vapor and runaway cyanide production forced astronomers to reconsider the chemistry of interstellar bodies. Neither solar system comets nor known interstellar visitors had displayed such selective metallic emissions or such rapid exponential increases in specific molecules. Theories range from deeply buried volatile pockets suddenly exposed by fracturing to unknown catalytic reactions driving the nickel release. But no model could yet explain why only nickel, and why the cyanide output would quadruple so dramatically in stepwise bursts. In the months that followed, Dr. Vukovic's findings fueled both formal publications and heated debates on astronomy forums. Some participants invoked exotic aggregation processes, perhaps electromagnetic fields concentrating nickel, or even speculative whispers of engineered materials. Most researchers, however, focused on the urgent need for new physics or chemistry to account for the data. The molecular puzzle at the heart of 3I/Atlas had become the central mystery, demanding explanations far beyond the reach of current comet science. Speculation flourished across online communities as the nickel anomaly and quadrupling outgassing numbers hit the public sphere. On r/space, threads ran for thousands of comments, with users posting diagrams of electromagnetic field lines and citing obscure papers on metal aggregation in cometary coma. One popular theory outlined how strong, transient magnetic fields could selectively concentrate nickel, leaving iron behind, a scenario dismissed as unlikely by most, but debated in earnest by late-night posters. Physics forums moderators pinned a summary thread warning, "No known mechanism explains the nickel-iron split. Please cite sources." Posts linking the anomaly to engineered alloys or Oumuamua's mysteries appeared daily, often flagged for removal with notes like, "Speculation without evidence, discussion welcome, but keep it grounded." A handful of regulars, some with academic credentials, weighed in to caution against premature conclusions. Dr. Lena S., an astrophysicist and forum contributor, wrote, "Extraordinary claims need extraordinary data. Let's see what JWST and VLT publish next." Meanwhile, a recurring meme about alien megastructures made the rounds, half in jest, half in genuine curiosity. Despite the noise, the community's appetite for new explanations was clear. Even as moderators steered conversations back to peer-reviewed models, the sense of standing at the edge of something unexplained kept users refreshing for updates, waiting for the next official release or telescope data drop. NASA's Planetary Defense Coordination Office convened an emergency teleconference on May 27, 2025, drawing in project leads from the Deep Space Network, Mars science teams, and the heads of both Hubble and JWST operations. The agenda was clear: ensure round-the-clock tracking of 3I/AT LOHAOS as it approached its closest pass to Mars, just 0.19 astronomical units away in October. On the call, PDCO Director Dr. Emily Hargrove instructed her teams to treat the event as a high-priority planetary encounter, even in the absence of any credible impact risk. Internal transcripts reveal a careful balance. Engineers debated how to communicate the comet's record-breaking mass without stoking public alarm, while scientists pushed for maximum data collection during the critical window. Within days, the Deep Space Network's 3 global stations, Goldstone in California, Madrid in Spain, and Canberra in Australia, were ordered to reallocate antenna time, patch scheduling software, and run continuous drills. Logs from the network's scheduler document a series of rapid micro-updates rolled out to manage antenna conflicts and guarantee seamless handovers as the comet crossed the sky. Each station rehearsed contingency plans for data dropouts, with technicians running simulated loss of signal events to ensure positional data would remain uninterrupted during closest approach. NASA's official statements emphasized that the trajectory posed no threat to Mars or any spacecraft, but the scale of the monitoring campaign was unprecedented. The agency's posture was one of vigilance and transparency. Every available asset focused on 3I/AT not out of fear, but to capture every possible clue as the comet swept past Mars. For the PDCO, this was planetary defense in practice, preparing for the unknown, even when the risk was only theoretical. By August 2025, verified data from Hubble and the James Webb Space Telescope showed nickel outgassing from 3I/Atlas ramped to 4.6 grams per second, while the comet's coma expanded from 13,000 to 18,000 kilometers in just days. The mass estimate now stands at 33 billion tons, an order of magnitude above any previous interstellar object. Cyanide production confirmed by the James Clerk Maxwell Telescope and the Very Large Telescope teams quadrupled to 4.5 times 10 to the 25th molecules per second by mid-September. Despite these unprecedented findings, the mechanism behind the selective nickel release and the absence of iron remains unexplained in published literature. NASA's Planetary Defense Office confirmed no collision risk as 3I/Atlas approaches within 0.19 astronomical units of Mars in October 2025. But its rapid variability led to a full-scale Deep Space Network monitoring campaign. While forum debates continue about electromagnetic effects or artificial origins, the scientific community agrees. 3I/Atlas challenges our understanding of cometary chemistry and interstellar visitors. For now, its true nature remains an open question, one that underscores the limits of current models and the need for continued observation.